All right, Calculus, welcome to your quick video here over your Chapter 4 quiz number 1, which is going to be not Wednesday of last year at this time, but Thursday this year here. And today we were brought to you by Chinatown, Coffee Espresso, and Fitbit, new sponsor for this video. Find the local max and min values of the function on the given interval. All right, so you're going to have to plug in -2 for x and 6 for x. And then we're going to have to find our critical values. Here you are going to get the square root of 22 over 9, which is the square root of 22 over 3. Square root of 9 is 3. Plus or minus will work for both. Okay, sorry about that, but you're going to plug them in. And holy cow, your minimum is is that right? Your minimum is at 6, -509, and your max is at that one critical value there. All right, some of these have some pretty aggressive answers, so sorry about that. Take the derivative, set it equal to 0. That's the name of the game. You get 3 and 1, but notice that 1 is outside, so don't include 1. You're going to use your starting point and end point, 2 and 4, and then plug 3 in. Your max is at 4, 5. Your min is at 3, 1. Okay, this next one, you're going to have to use the product rule. All right, derivative of the first times the second plus the first times derivative of the second. My gosh, you get that. Set it equal to 0. You're going to rewrite this as that. Then you're going to move it over and do some cross multiplying, which I did down here. Okay. And you get 2/3. 1 is also a critical value because 1 makes your derivative undefined. Okay, so be careful there. So plug all those in. And let's see, did I give an answer on that? I did. Local min's there, local max is there. Wow, sorry about that. Okay, this next one. Again, some of your homework problems are like this, so hopefully you started early. Set the derivative equal to 0. 2 sine x equals 1 sine. X is 1/2, first, second quadrant, and it's 1/2 in the pi 6 family, okay? So plug in -pi, pi 6, 5 pi 6, and pi. And, just use your calculator to figure out which one of those are the biggest and smallest. There it is. Okay, honestly, I think after that it gets sort of quicker. Just all you gotta do on 5 and 6 is to find the critical numbers, okay? So take the derivative, set it equal to 0. Take the derivative, low d high minus high d low, all over the square of what's below. You get this. So critical value is when the denominator is 0, okay, critical number. So you're going to set this equal to 0. Plus or minus root 5 makes the derivative undefined, so that those are critical numbers. You don't have to plug them back in. That's what's nice. I'm not asking for min or max values. Set the numerator equal to 0, so multiply everything or divide everything by -1. Your other two critical numbers there, -1, -5. You can pause this whenever you need to. I'm going to try to make this relatively quick. 6 is, well, straightforward, folks. Just set the derivative equal to 0. You just get 1. It was pretty easy. Okay, find all values of c that satisfy the conclusion of Rolle's theorem on the given interval. So first, you do need to show me that f of a and f of b are the same number, and they're both 0. So then you simply set the derivative equal to 0. All right, which there is the rule. I'm sorry, there's the answer there. Again, I plugged in c for x, and I got that. And 9 is solidly in that interval. If it's not in the interval, it does not count. Okay, I know there's a lot going on there. That's why you're setting equal to 0, because it's the mean value theorem, which is a special case. All right, this next one, take the derivative, which is this. Set it equal to 0. You get -4. Again, they're both equal to 41. That's why it works. You do need to show me f of a equals f of b. All right. You don't have to write continuous and differentiable. Find all values of c that satisfy the mean value theorem. Here, f of a is not going to equal to f of b. So you just need to figure out what f of a and f of b are. There's f of b, there's f of a. All right, so set the derivative. take the derivative and set it equal to that slope. It's not going to be equal to 0. It's going to be equal to 50. Again, I just plugged in c instead of x. No big deal. It does factor, believe it or not. When you move the 50 over, set it equal to 0. Negative 5 is not in the interval, so it's just 11 over 3. 11 over 3. In 9 through 11, find where each function is increasing or decreasing. We got to, this is just the whole, over an entire, it's an entire graph. So find the derivative, set it equal to 0. 9 halves, 4.5, it's where it's going to transition there. So negative infinity, 9 over 2 to infinity. Use a test value, maybe of 0. If you plug 0 in for x here, it's going to be negative. So the derivative is negative. That means it's decreasing. If you plug like 5 in, it's going to be positive. So then, and then also, this is a parabola. It's going to go from going down to going up. That's kind of easy to see. All right, increasing on that, decreasing on that. Here, take the derivative, set it equal to 0. Does factor nicely. We do need to know how to use guess and check. All right, those are your 3 intervals. Again, I would use a test number here of like -3. If you plug -3 in, you get a negative times a negative, which is a positive. It's increasing. I would use 0 here. You get a negative times a positive, which is a negative. That's why it's decreasing. And lastly, I'd use 1 here. Positive times a positive is a positive. That's why it's increasing. So it's increasing on those intervals, decreasing on that. Okay, same thing here. Low D high minus high D low, all over the square of what's below. All right, so we're doing that. And we're cleaning it. Oh my gosh. If that's true, that's probably one we made an oopsie and skipped on. Okay, so if I give you one like this, first off, -4 is a critical value, all right? It's going to do something. It's an asymptote there. Hopefully this top would clean up better, and you'd have 2 nice critical values there. All right, we're going to skip number 11. Just know how to find those critical values. So 12 through 15 would be examples of find it all. You're going to have a few of these, not 4. Okay, so first derivative, second derivative test. Take the first derivative, set it equal to 0. You have 2 critical values of 0 and 2, which I put over here. First one, use a test value of like -1, 1, then 3. Anyway, that's where it's increasing, decreasing, and increasing again. Okay, and because it went from increasing to decreasing at 0, you're going to have a local max. Plug 0 in for x, and that will give you 0. I don't know if I put that anywhere. Yeah, it's right here. There you go. And it went from decreasing, increasing at 2, so that's a local min. All right, so that's everything the first derivative test can tell us, when it's increasing, decreasing, and when it's min or max. Then take the derivative, set it equal the derivative of the first derivative, so the second derivative, set it equal to 0. 1 is where it's going to change concavity. In the second derivative, plug like 0 in for x, you get a negative. Plug like 2 in for x, you get a positive. Concave down, -infinity to 1. Concave up from 1 to infinity. So it has an inflection point at 1, comma, plug 1 in for x. And the original function, -4. That's a very fair question there. Here's 13. Set the derivative equal to 0. You get 0 and 1 as your critical values. Right here is a little table. -infinity to 0, 0 to 1, 1 to infinity. Use like -1 for your first one. A negative times a positive, that's a negative, that's why it's decreasing. Use like 1/2, a positive times a positive, increasing. And use like 2, a positive times a negative, that's why it's decreasing. Okay, so it's increasing on those, decreasing on those. It's got a local min because it goes from decreasing to increasing at 0, 1. Just plug that into the original. It's got a local max because it goes from increasing, decreasing at 1. Plug that in for x, 2. Take the second derivative, set it equal to 0, that's 1/2. Okay, so there's the interval there, -infinity to 1/2, 1/2 to infinity. Plug 0 in for x, you get a positive. Plug like 2 in for x, you get a negative. And it's going to have an inflection point at 1/2. Plug that in for x, 3/2. Oh my gosh, here's 14, folks. All right, I think we know what we're doing. That's the first derivative. those are the critical values. Pause this whenever you need to. That's the table. All right. There's where it's increasing, decreasing. Local max and min. Again, plug those x values in for x. Take the second derivative, x equals 2. And that's everything with concavity and the inflection points. And then finally, we got another quotient rule. Low d high minus high d low, all over the square of what's below. Does clean up relatively well. At the top, you're going to get two critical values of 0, negative 16. Notice that negative 8 makes the derivative undefined. It is also a critical value. So notice how it really doesn't change. It keeps decreasing, but we're not going to say negative 16 to 0 because at negative 8, there is an asymptote. So we've got to break that up. So it's increasing on those two intervals, and it's decreasing on those two intervals. And let's see. Increasing and decreasing. So it has a local max at negative 16 comma something. Plug that in. And it has a local min at 0. Looks like 0, 0. Okay, then find the rest. I mean, I ran out of room there. Second derivative. Second derivative is a little involved. All right, you'd have to do low d high minus high d low, all over the square of what's below again. So we'll talk more about that one in actual class. All right, those are all the questions I have. This is Yak Math Videos signing out.